Hello everyone and welcome to Calculus BC. In today's episode, we're going to be discussing Chapter 7.1, which is integration by parts. It is going to be the newest integration technique that you are going to put into your arsenal. And basically, integration by parts is pretty simple. It's by parts, it's just a reversal of product rule. And that's all it is. I don't know why I felt like I had the need to capitalize the product rule and all that stuff, but that's okay. It seems like kind of an important thing. So let's revisit one of the other rules that we know, because we learned a lot of derivative rules in Calculus AB, and then we learned how to reverse only one of them via integration. We learned how to reverse chain rule when we were U-subbing. And so what were the fundamental tenets of chain rule? So if we're going to revisit chain rule real quick, I'll put this down here so it's not confusing. Revisit chain rule and U-subbing. And so what was it that made the U-sub so unique to chain rule problems? Well, if I gave you something that looked like this, like the integral of e to the sine x times cos x dx, the reason why this problem is so recognizably a U-sub problem is because we see a relationship between a function that appears to be on the inside of something else as well as its derivative being multiplied. So this one seems pretty obvious. I think u would have equaled sine x, and then du would have been cos x dx, which would have formed my linkage here to be replaced with du. And instead of e to the sine x, I would have had e to the u. And that would have been pretty easy to integrate, right? Because the integral of e to the u is itself. Slap on the plus c, replace the u. So we've got e to the sine x plus c as our indefinite integral. So that one seemed to make sense, right? We had a multiplication relationship between the pieces that were inside the integral, and they had this derivative relationship to each other. So that would hopefully make sense as long as you really understood chain rule and how the mechanics of that worked. The U-sub really was just a reversal of that process. But in today's episode, we're not talking about U-subbing. That would be too easy. That would be a trip back to the past. We want to keep moving forward here. Today we're going to learn about the reversal of product rule. So how does integration by parts work? And what does the setup for integration by parts even look like? And how can we even tell when integration by parts becomes a necessary component in our calculus integration? Well, I'll give you something that's kind of similar to that. And it's similar in the sense that you're going to have two terms that are multiplied. But for some reason, they don't seem to have much of a relationship with each other. It's not like I can U-sub this thing, right? If I did u equals x, du would be 1 dx, and so I guess I could do the integral of u, but the sine of x, I guess, could be replaced by a u with a du, but I'm kind of back in this position. There's not a whole lot that moved. I didn't make the problem any better. I didn't make it worse, but I certainly didn't make it better, so I don't think that's the direction we want to go. So when we see this multiplication relationship between the terms and they don't seem to have a relationship with each other, there's a pretty good indication that we're going to be using integration by parts on this one. So in the beginning of the episode, I mentioned that integration by parts is a reversal of product rule. And so let's review what product rule is. If I derived two functions that were being multiplied, depending on the order in which you do it, you guys all know I like the way I do things. It's because I do them. But the way I rhythmically do this product rule here is I do first unchanged times the derivative of the second plus the second unchanged times the derivative of the first. Some of you guys have this thing reversed. It's not a big deal. But the relationship between the derivative and the result is super important, because if this is true, if the derivative of f of x g of x is f g prime plus gf prime, then hopefully it stands to reason that if I integrated the f g prime plus g f prime dx, I would get itself back. So hopefully that makes sense. So what I'm going to do is I'm going to actually split up this integral real quick. I'm going to say this is f of x g prime of x dx plus a separate integral g of x f prime of x dx equals f of x g of x. And I'm just going to go and pick one to get rid of. And the way I'm going to do that is I'm going to go and just subtract that integral from either side. So I'll just choose to operate on this one. And again, similar to product rule, the order at which you subtract and stuff like that, whichever one you decide to subtract isn't going to matter. But I do like this one. I do like this one because there's kind of a rhythm to its simplified version also. So you have f of x g of x minus the integral of g of x times f prime of x dx. And this is it right here. This is the formula for integration by parts, this thing right here. But it tends to be a mouthful. And so what people tend to do is they tend to replace the f of x and g of x and the g prime with different letters. They say u equals f of x, and then they say that du is equal to f prime of x. They say that dv is equal to g prime of x, and v is equal to g of x. And so when you replace all of those things, what you get is the integral of, instead of f of x g prime of x dx, you have the integral of, looks like u dv, and that's going to equal, and this is where the rhythm comes in. It's going to be uv minus the integral of v du. And this is typically what I tend to see this as, uv minus the integral of v du. And so it's pretty much just kind of a plugging in kind of thing, as long as you understand your integration pretty well. That's kind of the gist of where this thing goes. Take a second and copy that down if you want to. I'm going to clean up the board, and we will get started with our first example. In fact, we'll probably just revisit this good old x sine x dx right here. So if I go ahead and revisit the x sine x dx, there are methodologies for this. It's not just randomly plugging stuff in. So what you want to do is you want to initiate a strategy on how you're going to select what you're going to select. And so typically what you're going to do is you're going to be selecting u and dv. So you will choose u and, u, lowercase, and dv. Now there is a criteria for u and dv. There is a wrong way you can do this. And so what you want to do is the u, right? The u is going to, you want that to decay. You want that to decay when you derive. You want that to, in other words, you want it to get smaller as you derive. The dv, and this actually is true for both u and dv. The bottom line is and people tend to worry about the intuition of what I'm about to say, but basically it boils down to don't make the problem worse. And that's it. It really boils down to this notion: don't make the problem worse, and you will tell very quickly if the problem starts getting worse. And so what I'll do is I'll do this example of the x sine x, and I'll do it correctly, and then I'll do it again, choosing a different u and a different dv, and you'll see how it gets worse. And so let's do it. So we're going to do the integral of x sine x dx. And again, I like to make this list: u, du, dv, and v. Again, I'm going to choose u and dv. So u, I'm going to do it right this time. I'm going to call it x. And how did I know that? I know that because I know for now, and I'll show you what happens when it gets worse. dv is going to be sine x. Now, here's where we got to be careful here, because what I'm going to do is I'm going to derive to move down to du. So that makes this thing 1 dx. But in order to get v, I have to integrate that. So I got to be able to integrate that thing in my head. Hopefully we remember that negative cos is the integral of sine. And I forgot the dx there. Sorry about that. And so now, at this point, once you've identified this stuff, it becomes pretty easy. So remember the formula. It's going to be uv, so x negative cos x. So I'll throw the negative on the outside, negative x cos x minus the integral of v. So that's going to be, again, negative cos x. du is 1 dx. So I'll just slap down a dx right there. And then what I get is I get negative x cos x. I'm going to kick this negative on the outside and call them plus the integral of cos x dx. And what I get is I get the integral of cos x is going to be sine x plus negative x cos x and then plus c. And that's how this thing integrates. Now, if you don't believe me that this would be the integral of x times sine x, I don't believe you. Let's rederive it and see if I'm actually correct. So if I do d over dx, I'm just going to check my work now. Negative x cos x plus sine x plus c. Of course, if I derive this guy out, the c is going to go away. I'm going to get negative parentheses. I'm going to do product rule here for the first term. So it'll be first unchanged times the derivative of the second plus second unchanged times the derivative of the first plus cos x. The c is going to go away. So now I'm going to go and distribute that negative in. I get x sine x minus cos x plus cos x. And notice how the cos x's are going to make like a tree and get out of there. Hey, check it out. I've got x sine x back, which is what I started off with in the beginning. So hopefully that makes enough sense with this example. Now, I told you guys I would do this problem again just to show you what it looks like when the problem gets worse. I will not back down from that. Let's see how the problem gets worse if we choose the wrong x, if we choose the wrong u and the wrong dv. So x sine x dx again. So again, just u, du, dv, and v. So when I talked about the derivative of u having to decay, well, it's hard to tell because it seems like if I chose u as sine x, I would get cos x. That's not a bad derivative. But if I chose x as dv, right? Remember, we choose the u and we choose the dv. Now I've got x squared over 2. And, you know, I'm looking at this. I'm not feeling the x squared deriving into anything with the, into that. But, we could be wrong. So it goes x squared over 2 sine x minus the integral of v, so x squared over 2 du cos x dx. And oh my goodness, do you see how the problem now gets worse? This is terrible because this situation that I have in this weird looking piece of tofu here, it's definitely worse than what we had. We're in a way worse position now than we were a few minutes ago. So this, I think, once you've chosen the wrong u and dv, just back out and try it all over again. These should click together quite well. And so if you make that mistake, just back out and try it all over again. Give me a second. I will be back with the next problem. Sometimes you're going to be forced in a situation to where integration by parts alone may not be enough. And that's why it's really important to be able to tell if you're actually making the problem worse or not. So remember, the important thing about the u is that it has to decay. So as long as you did that, as long as the u to du movement got smaller in degree power, you're going to be fine. And so in this example here, you're going to see the problem not resolve itself entirely quickly. But that doesn't necessarily mean the problem got worse. It just means the problem got better, but not better fast enough to where we could actually do something about it. So let me show you what I mean by that. U, du, dv, and v and dv. And if you want, go and take a second and pause and try and guess as to what you think u and dv are going to be. I'll give you a few seconds here. Hopefully, you were able to determine that x squared is u, and dv would be e to the x. So integration of e to the x would be e to the x. I keep forgetting the dx here. Sorry about that. This will be 2x dx. And now from here, let's just hack the formula here. So we've got uv, so x squared e to the x minus the integral of v. So that's going to be v. So e to the x du is going to be 2x dx. Now the 2 is a constant. I'm going to kick him out. So x squared e to the x minus 2 integral x e to the x dx. Now, let's pay attention to this little spot right here. That's not a u sub. If only this thing was x squared on the inside, I could have u subbed it. But that's unfortunately just not where we're at. So this one here hasn't resolved itself quite yet. I've got to do integration by parts again. So from here, what I'm going to do first is I'm going to carry down the pieces that are not going to be reintegrated. So I know it's going to be x squared e to the x minus 2 times something, right? And that something is going to be the result of my second round of integration by parts. So it'll be u equals, I'm going to go x du is going to be 1 dx. dv is going to be e to the x, and v is going to be the integral e to the x again. Hopefully you were able to figure out what the u and the v were. And then again, I'm just going to do it one more time. So it'll be uv, so x e to the x, minus the integral of v, so e to the x. Look at du. He's just a 1 dx. That makes stuff super easy for us now. So now what I get is x squared e to the x minus 2 bracket x e to the x minus e to the x, and then plus c. And feel free to leave it like that if you want to, or distribute the 2. It is entirely your choice. And so notice how that required 2 rounds of integration by parts. Sometimes that's going to be a thing, you know, be on the lookout for it. You know, and it's not really that terrible. Like I said, the hardest part is choosing the u and the dv appropriately, but I don't, you know, after a while you kind of start to get the sense of when the problem's getting worse and when the problem's not getting worse. One of the consequences of learning integration by parts is it allows us to integrate things that we wouldn't otherwise think of. Like, for example, if I give you an example 3 here, the integral of ln of x dx. Now, the most common misconception is people are going to put 1 over x, but that's not true. The derivative of 1 over x, the derivative of ln of x is going to be 1 over x. The integral of 1 over x is going to be ln of absolute value of x, right? But we have to integrate ln of x now. So how do we do that? Well, this is when integration by parts actually comes in. And so from here, I'm going to go and list off u, du, dv, and v. Now, again, I'll give you a few seconds. Try and guess what u and dv are. I'll give you time. If you need more time, go ahead and pause. Now, obviously, ln of x going into dv would be terrible, because if we could put ln of x into dv, we'd have to integrate it to get to v, but if I could integrate ln of x, I wouldn't have to care about this problem, right? So I don't think that's appropriate. I think that ln of x is best put right here, because when we derive it, it becomes 1 over x. Now, what could then fill the role of dv? Well, there's nothing else, right? Well, except there's actually a 1 dx there, and if I integrate that 1, I get x. So how do we do this? It's going to be uv, so x ln of x minus the integral of v. du is 1 over x dx. Check this out. They cancel. So you end up with x ln of x minus the integral of 1 dx. So it's x ln of x minus x plus c. Now, don't just take my word for it. Let's rederive this thing and find out if he's actually what we want him to be. Well, I see a little bit of product rule here. So first unchanged times derivative of the second plus second unchanged times the derivative of the first minus 1. So then those guys are going to go away. I got 1 plus ln of x minus 1. Those guys cancel. I've got ln of x. Hey, I'm back to where I started. Awesome. After a while, you'll start to remember that the integral of ln of x is this thing, because you'll do this so many times. But for now, let's go ahead and show the work on how we get the integral of ln of x using our good old buddy integration by parts. I'll be back with the next example. Give me a second. All right, in this next example, we're actually going to be doing a couple of things. There's a couple of things that make this problem a little difficult. First off, it's a definite integral, and so we can't study a new integration technique without learning about definite integrals again, right? And so the idea is going to be the same. I'm going to integrate this guy, obviously using integration by parts, and then I'm going to plug in my intervals from 0 to 1. And so that's not what makes this problem a little tricky, though. What makes this problem a little bit tricky is there's going to be a step in the middle of this that you guys are going to recognize, and you're not going to want to recognize it, but you will. So we're going to list off our pieces here. So obviously u is going to be tan inverse. du is going to be 1 over 1 plus x squared dx. dv is going to be 1, just like it was in natural log, and then so 1 dx, and v is going to be x. So that's going to be uv, so x tan inverse x minus the integral of v times du. So that's going to be 1 over 1 plus x squared dx, and I'll go and just call this guy from 0 to 1. Okay, so from here, let's go and simplify the inside of the integral real quick. So it's going to be x tan inverse of x minus integral from 0 to 1 of x over 1 plus x squared dx. Now, a few seconds ago, I mentioned that there's going to be a move in the middle of this problem that you're not going to want to recognize. Because right now you're probably thinking, wait, we're in integration by parts. There's, like, what else are we doing here? Well, I'm going to take you back to the past, and I'm going to highlight this yellow cloud right here. And I want to draw your attention to the fact that we can't integrate this thing right now without another integration technique. And so what I'm looking at is I'm looking at a function, and I'm seeing its derivative being multiplied in. So if you haven't guessed it already, here it comes. It's this guy. It's the u sub, okay? And then du is going to be 2x dx. Yes, so u subs have made their triumphant return. Now, ordinarily, when it comes to u subbing with definite integrals, I tend to replace the limits of integration. However, since I'm only integrating this portion here on the right side and everything else is in terms of x, this is going to be one of those times where I'm not going to do the limits of integration replacement. Instead, what I'm going to do is I'm going to create a side work deal here. And you're going to want to do the same thing, because if you use these limits of integration, like if you, I'll just go and proceed forward as if I'm doing this wrong. I'm going to integrate this thing. I get 1/2 du equals x dx for my linkage here. If I call him 1/2 on the outside, right, and then 1 over u du, if I leave the 0 to 1 in there, I'm actually going to get marked off by College Board, and I want to make sure that you guys don't do that. So that is going to be something that we're not going to do. It doesn't make sense to put x limits of integration on a u-style integral. And I'm not going to replace the limits of integration because I still have x's in my ultimate integral. So this is just side work here. I'm just going to go and say this is on the side. And so what I've got is I've got 1/2 ln of absolute value of 1 plus x squared, but I don't really need the absolute value there. The 1 plus x squared is always positive, so I can just call him 1/2 ln of 1 plus x squared. That is going to be what goes inside here. So I'm going to get 1/2 ln of 1 plus x squared on the interval 0 to 1. But please don't forget about this guy. He was always there. And it's going to be minus that. And so from here, we are going to go ahead and reevaluate this idea on 0 to 1. So what I've got is I've got 1. Whoops, forgot about the x there. Sorry about that. 1 times tan inverse of 1 minus 1/2 ln of 1 plus 1 squared. That takes care of the 1's, minus 0 times tan inverse of 0 minus 1/2 ln of 1 plus 0. Okay, that's a lot to take in, but we can go ahead and do this. Luckily, this guy is 0. ln of 1 is also 0, so the entire right side is gone. Tan inverse of 1 is going to be pi over 4 minus 1/2 ln of 2. And I think that's going to be as far as we can go with this integral. So realistically, the definite integral part wasn't really what I needed you guys to understand, because we always integrate, plug in the upper bound, the lower bound, subtract the two. It was really that sometimes these u subs can be sneaky and pop themselves in when we least expect it. Don't forget about those old rules since you've learned this new one. There's going to be an incorporation of u subs that happen, throughout integration by parts from time to time. So just, when it happens, don't think you've done something wrong. I'll be right back with the last and final example. All right, here we go. This is probably one of the most deceptive problems until you kind of unveil it. And once you unveil this problem, it's actually pretty easy to predict. You kind of see it coming once you kind of see how this thing unveils itself. E to the x cos x. This is going to be one of those times where I don't know if the choice of e and of u and dv actually is going to make much of a difference. So I'm going to go with what makes my life easy in the beginning. I'm going to just make e to the x u, and then I'll make cosine x dv, right? Because if I integrate cos, I get a positive sign. If I derive e to the x, I get e to the x. So seems okay so far. Nothing out of the ordinary so far. U dv minus the integral of v. So sine x e to the x du, right? Okay, well, we've been in this situation before where we have to, I'll go and clean them up a little bit. So e to the x sine x minus the integral of e to the x sine x dx. And so nothing too crazy here. We've been in the situation before where we've had to integrate by parts twice. So it's got to do it. So u, du, dv, and v. So we're going to pay attention to this guy here. So u is going to be e to the x again. Du will be e to the x dx. dv will be sine x dx. The integral of sine x, be careful, is negative cos x dx. So again, we'll just go e to the x sine x minus one big hunkin' bracket here. So uv, so negative e to the x cos x. I just flipped the negative on the outside of the e, minus the integral of v, so negative cos x du is going to be e to the x dx. Okay, let's clean him up a little bit, and I think I'm going to draw your attention to something odd that has happened afterwards. So this is going to be e to the x sine x. I'm going to distribute this guy in, and that's going to become plus e to the x cos x. Now, this negative and this negative will become positive, but since he's being subtracted, he's actually being negative, right? So hopefully that makes sense here. So we got negative e to the x cos x dx. Well, I want to draw your attention to this part of the problem right here, because if you notice, this is where we started. So if I do integration by parts again, I'm just going to end up with it again and again and again. This is deja vu right here, right? We've been in this place before. And so the cat walked by the door, we looked and it shook, and then we looked again, the cat walked by and shook again. And if you understand that movie reference. So how do we deal with this situation here when we end up in this deja vu situation? Well, remember, what we do here is we have to remember that the original formula for integration by parts was the integration of u dv equaled, right, uv minus the integral of v du, right? So this formula here is supposed to give us a result. It gives us the integration of two things being multiplied that have no relationship to each other. So this whole shebang here is equal, right? This is supposed to be the result of the original integral. So that's going to be e to the x cos x dx. And what I'm going to do is I'm going to go and solve for that expression. And I'm going to do that by adding the duplicate over. And what I get is e to the x sine x plus e to the x cos x equals 2 of these integrals of e to the x cos x dx. And again, I'm trying to solve for the expression, right? So I'm going to go and just divide everything by 2. And what I end up with is the integral of e to the x cos x dx. I'm just moving the result to the left side, so this guy's going here. So I'm just changing sides here. And that's going to equal e to the x sine x plus e to the x cos x all over 2. And don't forget that plus c. So this is what happens when you end up in this rampant cycle of integration by parts. Now, I told you that it's actually pretty easy to recognize once you see it coming, and I'm hoping that you guys will recognize it pretty quickly too. And that is when you have a situation that looks just like this. Because there's a repetitive nature about these guys as derivatives relationships, right? E to the x, if you derive them a million times, you get e to the x. Cosine, you end up with sine or cosine, and if you derive sine, you end up with sine or cosine. So there's this cyclical nature about both of these functions that makes this an inevitable deja vu type problem. So when you see this problem, just know that you're going to end up having to solve for the original expression at some point in the game. So hopefully integration by parts makes sense. As always, please leave comments or questions in the comments area. I will see you all in the next episode.